Now we will tackle on the steady state flow process as a continuation of our first law. Since we already derived the general equation, so let's now continue on the steady state, steady flow process. So it is a process during which a fluid flows through a controlled volume steadily is called steady state process. A large number of devices as turbines, compressors, and nozzles operates under the same conditions for a long time and can be modeled or classified as steady flow devices. The term steady implies no change with time. The term uniform implies no change with location over a specified region. So, steady flow process, there are considerations. Number 1, no properties within the control volume change with time. Thus, volume, mass, and energy of control volume remains constant. As a result, the boundary work is zero. Also, total mass entering the control volume must be equal to the mass leaving the control volume. Second, no properties change at the boundary of the control volume with time. It means that the mass flow rate and the properties of the fluid is at an opening must remain constant during a steady flow. And lastly, third, the heat and mass interactions between the control volume and its surroundings do not change with time. Okay. So it states that for steady state steady flow process, the mass entering is equals to the mass leaving. So considering here the equation of our conservation of mass, wherein we have mcv with respect to time plus the summation of mass leaving minus summation of mass that is entering, this is equal to 0. Since there is no mass inside the control volume, so we let this 0 here. So therefore the summation of mass leaving the control volume is equals to the mass entering the control volume. So this is the condition on the steady state, and the energy of our control volume with respect to time, by definition it is also 0. Okay, so applying the first law, so our first law becomes Q CV plus the summation of mass that is entering, this is HI plus VI squared over 2 plus G ZI. This is equivalent to the summation of mass that is leaving. This is HE plus VE squared over 2 plus G ZE, and plus work of our control volume. So this will be the equation now for our steady state steady flow process, wherein the mass that is entering is equivalent to the mass that is leaving. So there is a conservation of mass here. Okay, So for example, we have here a pump. Okay, so if I have a pump, so it draws water to a reservoir here, and in order to operate the pump, of course, it needs a work input. And we have also here the this elevation here. This elevation, this is ZE. And here, this is ZI. This one. This is ZI. Okay, considering this is our reference point here. Reference point. Okay. So conservation of mass, the mass that is entering here is equivalent to the mass that is leaving. You know that the equation of mass could be this one, m times the density times area times the velocity here times that velocity. So mass flow rate here is area times velocity. This is area times velocity over this specific volume. It is the reciprocal of our density is the specific volume. Specific volume V. Okay. That is for pump. And for the nozzle, for example, you have this nozzle here. So you have this nozzle. Okay, this is the exit, and this is our inlet here. So obviously our Z or our elevation here is ZI. This is equal to ZE. Okay, and the mass entering, of course, is equivalent to the mass leaving by the conservation of mass. Okay, so the general equation of our first law becomes, considering this nozzle and considering steady state, steady flow process. So this will be QCV plus MI HI plus VI squared over 2 plus G ZI, and ME, this is HE plus VE squared over 2 plus G ZE. Okay, so for a nozzle, it is adiabatic, meaning the QCV is equivalent to 0. This is adiabatic, QCV is equal to 0. Okay, QCV is equal to 0. So this is 0 here, and take note that the mass entering is equivalent to mass leaving here. So we can write this one by another thing, the ZI here is equivalent to ZE. So this can be cancelled here. So what remains is this one. This this MI is equivalent to HI plus VI squared over 2. This is VI squared over 2. This is equivalent to ME. This is in mass flow rate here. Okay. So because at the exit there is no velocity, the velocity here is 0, and we have also no enthalpy. The enthalpy becomes 0. Okay, so this is our equation for a nozzle considering a steady state, steady flow process. Another thing, if you have a turbine, so if we have a turbine, so this is the inlet and this the exit here. This is our work. Turbine will generate work. Okay, and of course our MI is equivalent to ME for a steady state, steady flow process. Okay, so our general equation becomes this one, QCV plus MI times HI plus VI squared over 2 plus GZI. This is I. Is equivalent to mass that is leaving times HE plus VE squared over 2 plus GZE plus the work of control volume that is being generated by the turbine. And also for a turbine, this is also adiabatic, wherein Q CV is equal to 0, adiabatic process. Okay, so if here, if the delta KE, or the change in kinetic and potential energy, is 0, okay, so the work of our turbine here, so this is 0, this 0, and also here this is 0 and this is 0, so also this Q is 0. Okay, so the work of our control turbine, this would be the M, since M is equivalent to MI and ME. So m times h I minus h e. Okay, so our general equation becomes this one. Okay, considering a turbine and this steady state, steady flow process. Okay, so that's all our discussion for the steady state, steady flow. If you have some questions or any clarifications, just leave a comment, and see you in the next video. Thank you.